I didn't know, I didn't expect. 49th lecture. We made some mistakes yesterday when we will have to make that correction to Gilbert cell analysis. There was a small mistake, but I found out that the source from which I extracted the material did have that mistake. It was not my mistake, but I should have taken it carefully. And then after this correction, we will go to operational amplifier imperfections. This I believe has never been taught to you. In the 110 class, in the previous class, we simply took the op amp as an ideal one and showed its applications in various situations. But this is very important. This is a very important topic for an electronics engineer. Operational amplifier is the most often used linear analog integrated circuit, and one should be careful. The corrections are as follows. If you turn your page and look at the basic Gilbert cell, the circuit is the same. We didn't make a mistake in the circuit, but in the assignment of the currents IA1 and IA2, we had written this as XIA and we had written this as 1 minus XIA, and then the differential input current had a DC component, had an IA component, which is the mistake. You know, if there is no signal, then X is 0. This X is signal induced, and therefore of the IA, as I had shown you earlier, that was also a differential amplifier with a current source biasing IA. Half of it should go to one of the transistors, half of it should go to the other. When there is a signal, that is, an unbalance is created between the two base voltages, then one of the currents increases and the other decreases. The one for which VBE increases, the current increases; for the other it decreases. Now X could be positive or negative, but the sum of the two must be equal to IA, and the difference must be only proportional to the signal induced quantity. Okay, the difference between them is 0 if there is no signal, and therefore the difference must be proportional to the signal induced quantity. The differential input current is obviously twice X times IA. Okay, so this is one of the corrections. And then this continues in the analysis. Where do IA1 and IA2 come from? Well, as I had drawn this circuit, the circuit is the same except that these two currents are half plus XIA and half minus XIA. That is the correction. So in the second diagram that you drew yesterday, please do indicate these corrections. Then the differential input current is twice XIA. There should not be a DC component in the differential input current. And as I said, this is a voltage to current converter. Gilbert cell essentially is a current amplifier, current to current, and since our obsession is with voltage amplification or voltage signal processing, we have a voltage to current converter at the input. The input is applied between the two bases, and that is what causes an unbalancing of the two current, plus X and minus X. In the analysis, to review quickly, the current I1, can you see this part? Yes, sir. The current I1 is the collector current of Q1, and therefore this is related to Is e to the VBE1 by Vt, and this is the same as IA1 ignoring the base current of Q2. Beta is high has been assumed. Then I1 by I4 we had shown, or I4 by I1 we had shown that this is VE1 minus VE4, and this is the voltage V1 defined as V1 applied between the bases of Q2 and Q3. And for by a similar argument we show that I4 by I1 is the same as I2 by I3, because VBE2 minus VBE3 is also equal to V1, E1 and E2 and E3 being a common point. Okay, so the ultimate relationship is that I2 by I3 is equal to I4 by I1, which is the same as IA2 by IA1. So instead of x by 1 minus x, it is half minus x IA divided by half plus x IA. Okay, make this correction, half minus x IA divided by half plus x IA. And then we add 1 to both sides. Add 1 to both sides, so we get I2 plus I3 by I3 as equal to 1 by half plus x. I hope I am right. When I add 1 to this, I get 1 by half plus x, which is the same as I2 plus I3 is the total emitter current, IE, and therefore this is IE by I3, which gives me I3 as equal to IE half plus x, and the rest of it goes to I2, that would be IE half minus x. In other words, the proportioning of the current is the same as in the input current proportioning, is the same, and the two output currents are I1 plus I3. This is half plus x IE plus IA. This is the total bias current IE plus IA, and the other output current I2 plus I4 is half minus x IE plus IA, and therefore the differential output current should also be proportional to the signal. It is twice x IE plus IA. There is no DC component. That is the mistake that we had made, and therefore the current gain is 1 plus IE by IA. In this analysis, we did not consider frequency effects at all, and the analysis only assumed that beta is much greater than 1. In practice, we can go up to beta equal to 10. Even then the analysis would be valid. Also, you notice that in this analysis, we did not assume the size of the signal. We did not put any restriction on the size of the signal. So this gain should be valid even for large signals. That's another advantage of current signal processing. Okay, even for large signals, this gain should be true. And this is the basic widebanding by Gilbert cell. The total circuit, the complete circuit, now I shall draw. Please try to draw with me. The complete circuit in which a voltage is the input and a voltage is the output. Okay. The circuit is like this. You have the two transistors Q1 and Q4, the two basic transistors, and instead of taking the current as the output, since we have to take the voltage, we add a load to both. This goes to plus VCC. The currents are converted to voltages, and therefore your output signal would be the differential signal here, V0, let's say plus minus. You can assign some polarities to this. Q1 and Q4 both are, the bases are connected to ground, and in addition you have the internal differential amplifier Q2 and Q3, the emitters of which are connected, and this is connected to an I sub E to minus VEE, and they are connected in a criss-cross fashion. That is, the collector of Q1 is connected to the collector of Q3, okay, and the collector of Q2 is connected to the collector of Q4. This is the basic circuit, and in addition the emitter of Q1 is connected to the base of Q2, yes, and the emitter of Q4 is connected to the base of Q3. Okay, this is the criss-cross connection, and these are the currents which are half plus x IA and half minus x IA. These are the two currents, and these currents are derived from a voltage to current converter, and it is like this. You have two transistors Q5 and Q6. Then there are two small resistances. Nobody asked me why these resistances are there, RE and RE. Okay, you connect the voltage source, the signal source here, VI, here between the two bases, and that is converted into two currents, half plus XIA and half minus XIA. Obviously I sub A is the current generator that goes here, I sub A.
Excuse me, sir. So in case beta is less than 10, so in that case what do I take instead of half plus XIA and half minus XIA? I have to take the base current into account as well.
Now here, you see, as far as these two currents are concerned, they are not affected by beta.
So the total will not be equal to IA, that will be less than IA in that
That's
case.
right. If this current, IE1, if beta is less than 10, then IE1 cannot be equated to this. Then the whole expression shall change. The whole expression shall change, and you will not get the gain 1 plus IE by IE. Now beta will be less than 10 at very high frequency, and therefore the expression shall not be valid at high frequencies. That's all that it means. In other words, the gain at high frequencies will decrease. Okay.
Why do we need minus V below I?
Why do I need this? Well, you know that in an op-amp, in a differential amplifier, there are two supplies that are needed.
Even IA is going to minus V.
That is also going to minus V, yes. This is also going to a negative supply. As I said, this is not essential, but I have also explained the reason why two supplies are used. In an op-amp, in an IC chip, there is no ground terminal, there is no reference. An op-amp does not provide a reference. It provides several terminals, input 2 terminals, output 1 terminal for positive supply, 1 for negative supply. Where is the ground then? The reference is between the common point of the two supplies, plus VCC and minus VCC. Usually they are equal. Okay, and therefore since two supplies are available, and the differential amplifier is based on that. With two supplies,
So then what about the basis of Q1 and Q2?
what about the basis of Q1 and Q2? These are grounded because, yes?
So then we'll just take ground in the IC then.
Oh, this have to be connected to, you see, these two bases will be connected together, and a terminal will be brought out. In the IC chip of the Gilbert cell, a terminal will be brought out which you will have to connect to ground. Right? You will have to do that externally. There is no ground supplied in the IC chip. Okay? Now, this is the total circuit. This is the chip that is available. Now, there are modifications, and very simple modifications. One of them is that these loads may not be actual resistances. If you want a very high gain, then these loads will be replaced by an active load, a current source. Okay. In a similar manner, Q1 and Q4, the betas, if they are not adequate, then you might use a Darlington here for Q1 and Q4. This applies to Q2, Q3, Q5, Q6 also. The chips will cost more, but it's a much better voltage amplifier, much better wideband voltage amplifier, because if betas are less, you increase the betas.
So even if beta is appreciable, I put Darlington pair, beta square, effective beta becomes. Does the FT increase and FH increase?
Does the FT increase? No.
FT
Beta
increase
square-
and FH, will the FH increase?
Tell me?
Will the FH increase?
FH will increase. FT will not increase.
FT like this.
FT will not increase. Okay, any question on this? Now we go to the operational amplifier imperfections. These are the most popular IC chips, the Gilbert cell. Gilbert cell is used for many other purposes also. Operational amplifier imperfections. Are you having a control course now? Next semester, okay. As you have learnt earlier, an op-amp It's very convenient to view it as an ideal device. There are two inputs, non-inverting input, inverting input. The gain is A, and the usual thing that you write is V0 equals to A V1 minus V2. Now this, there can be nothing more untrue than this relationship. This relationship, although it's very simple to write and simple to manipulate, has many imperfections. And these are the imperfections that one has to be careful about if one uses an op-amp. The first imperfection is that capital A, we assume this to be infinity. Hardly ever it is more than 10 to the 6. A must be the usual op-amp that you get in the market. If you get anything less than 10 to the 4, you reject it. It will be useless. Okay? It must be much greater than 10 to the 4. In fact, 10 to the 6 is an approximate figure. Number 2, you see that we assume that the op-amp does not take any current. That is, the input impedance Ri1 at V1, we assume this to be infinity. We also assume that Ri2 tends to infinity. But we know that the input stage of an op-amp is a differential amplifier. And a differential amplifier, at the base, the impedance is not infinity. It always takes a base current. Okay? And the usual figures are of the order of 10 meg, practical figures. The differential input impedance, that is between V1 and V2, is also of the same order, 10 meg. That makes a good op-amp. The CMRR, we have assumed that if V1 is equal to V2, then V0 equal to 0. This relation says that if V1 is equal to V2, it is 0. Now, you know from the first stage, the differential amplifier, that CMRR is not infinity. Our ideal value CMRR is infinity, but in op-amp, usually the CMRR is greater than 70 dB, not more than that. There is a common mode gain, but the common mode gain is small enough and the ratio is approximately 70 dB. The most shocking thing about op-amp imperfection is that you assume the bandwidth. You assume that not only the gain is infinity, but the gain is infinity at all frequencies. The bandwidth ideally is of the order of infinity. In practice, the high frequency 3 dB point is of the order of a few tens of hertz, and 10 hertz is not an uncommon figure. This is the most shocking imperfection that an op-amp has, and it is necessary to have this imperfection. The question is, how do you use an op-amp then at 100 kilohertz or 200 kilohertz? What we do is we apply negative feedback to decrease the gain and increase the bandwidth. The gain bandwidth product, for example, if you have a gain of 10 to the 6, then GBW is 10 to the 6 multiplied by 10 hertz, that is 10 to the 7 hertz. So if you want a gain of 10, then you can go right up to 1 megahertz, no problem. This is how it is done. But the high frequency 3 dB point of necessity has to be reduced to a few tens of hertz. Even if you can design an op-amp with differential amplifiers and other stages, we will come to the architecture a little later, but of necessity it has to be reduced. We will see what the necessity is. We also assume that the input differential amplifier is, the transistors are perfectly matched, which never is the case. If they are not matched, then what will happen? The VBE1 and VBE2 would be slightly different, and therefore even if there is no signal between the two bases, you shall have a DC signal, alright, which is called an offset voltage, input offset voltage. This occurs because the two VBE1s are not exactly identical, so that even if there is no signal, there appears a voltage between the two bases. It's usually denoted by the symbol Vi0, and in practice it must be less than about 10 millivolt. The less the better. And you have seen that in some of the differential amplifiers a small emitter resistance Re is attached. For example, in the last Gilbert cell also, the voltage to current converter, we had an Re. Okay, this Re is usually used to balance the two transistors. Even if they are slightly mismatched, a small resistance used here, and this will be part of the fabrication. It is adjusted like that. Even with that adjustment, you may have an op-amp in which there is a voltage, input voltage offset. However, in the Gilbert cell, nobody asked me this question. Suppose we take away the Re. Suppose the transistors are completely matched. We take away the Re. What is the harm? Why was that used? It's a voltage to current converter. That is the clue. If it is a voltage to current converter, what kind of input impedance do you want? High input impedance. And if Re is not there, then what is the input impedance? Twice R pi. That's all. So Re adds to the input impedance by the amount beta plus 1. This is why Re is used in a voltage to current converter. Is the point clear?
So, but if Re is a small resistance of the order of a few ohms,
Huh?
then your beta
It will not be of the order of a few ohms. In a voltage to current converter, you will increase, you will use a sufficient, because the purpose is different. Purpose is not to balance the offset. Balancing offset requires a small resistance. But there is no harm if you use two large resistances on the two ends. They can be slightly different to balance the offset. Alright. The purpose of Re in a Gilbert cell, voltage to current converter, is different. It's to increase the input impedance. Okay. Similarly, if the two bias currents are slightly different, IB1 and IB2, if the two bias currents are slightly different, then there exists a differential input offset current. Okay, there can be an input offset voltage, and if it is a current amplifier or voltage amplifier, okay, this will produce a signal at the output. Even if there is, this will produce an output even if there is no signal input, and therefore you have an input offset current, which is the difference between the two bias currents. It is denoted by II offset, input difference between the two bias currents. These are very small, of the order of 0.2 nanoampere, but it can cause a great harm to the operation of the operational amplifier. It can reduce the signal to noise ratio because of the existence of a DC input offset voltage. Okay, one has to be careful about these imperfections. Now we shall look into each of these imperfections and see how they can be annulled in a practical circuit and how their effects can be minimized. At this point, it would be good to see what the usual architecture of an op-amp is. What one does is, you know, the input stage is a differential amplifier. We show it by a block. Input stage is a differential amplifier. There is an inverting, non-inverting input, and there is an inverting input. Okay, differential amplifier. You may have a couple of them. A differential amplifier is direct coupled, and the two collector outputs can be taken to the next stage of the differential amplifier to increase the gain. But what is the property of a differential amplifier? What about the output impedance? Input impedance can be made high if you use those two Rs. Output impedance is usually large, and therefore it's a voltage to current. In other words, these are transconductance amplifiers. Is that correct? There is a high input impedance, and therefore what one does is, after one or two of these differential amplifiers, the 741 for example has two. there are some others which also have 2. The output is then well, usually you take a single-ended output from a differential amplifier. You don't take both, you don't take the difference unless you want to apply it to another differential amplifier. Okay, so a single-ended output, and then another gain stage is attached. Another gain stage is attached, and this gain stage usually is a compound connection. We have already, the 741 for example, has a CC-CE combination, common collector, common emitter. This also aids in broadbanding, but it also supplies a gain. The input stage is CC in order to match a current amplifier to a voltage amplifier. Okay, so the input impedance is high, and then the output is a common emitter stage. Now, usually a capacitor is attached from the input to the output, a capacitor C. This capacitor is called, for reasons to be discussed a little later, a compensating capacitor, sometimes called frequency compensating capacitor, and it is this capacitor which brings down the 3 dB point to 10 hertz, several tenths of hertz. Because you see, differential amplifier gain stage, we can design them for several megahertz cutoff, but usually a capacitor is attached from the input to output to bring down the 3 dB point to several tenths of hertz. How does it do it? You see, it happens because of Miller effect. There is a large gain, and therefore this capacitance reflects at the input as a large capacitor, and the time constant determines the actual 3 dB point. Okay? Pardon me? Why do we do it? We will come to this a little later. The next stage, you see, the gain stage, the output of this, there is no capacitor inside, there is no coupling capacitor. Well, this capacitor is usually supplied by the manufacturer, or sometimes 2 terminals are brought out in an op-amp and called compensating terminals, where you have to connect a capacitor externally depending on where you want your 3 dB cutoff. We will come to this, but at the output, you see, in the DA, neither in the DA nor in the gain stage there is any coupling capacitor, and therefore the output may have a DC level which cannot be applied to the next stage. What should be the next stage? The last stage? Last stage should be common collector, and usually if the op-amp is to deliver power, then this is a class B common collector amplifier. You remember the class B complementary symmetry transformer less amplifier. Usually that is the last stage. Almost all op-amps have that kind of a. But the point is, suppose this is at, let's say, 5 volt. You cannot apply 5 volt to a base. You remember the class B, there are 2 transistors, PNP, NPN, and the bases are connected together. You cannot apply that voltage. So what is needed, this we have not discussed so far, what is needed is a level shifter. We shall discuss this in details. A level shifter. The DC level has to be shifted such that the overall output of the op-amp is equal to 0 when the signal is 0. Alright? And such that it does not affect the operation of the next stage, which is usually an emitter follower but connected in class B complementary connection, and that is the output. The output goes to a load. This is the general architecture of an op-amp. The first stage, the first block is a transconductance amplifier. The second block is a voltage gain stage, usually a CCCA combination, and then of necessity you have to have a level shifter. Finally, an emitter follower which has to deliver the power to the load. Even if power is not important, emitter follower is necessary to reduce the output impedance to a negligible level. several tens of ohms. This was one of the imperfections which it did not mention. The output impedance, we usually assume this to be 0, but of the, in an actual op-amp it's of the order of several tens of ohms. Okay, 100 ohms is not very uncommon. Alright, now let's look at DC level, this level shifter. But before the level shifter, let us recall that in the DA as well as in the gain stage, you don't use any external resistance for biasing. For biasing you use a current source, and you don't use any external resistance for the load resistance. You use an active load. So both of them use active load and current source biasing, those current mirrors. Let's look at level shifting. There are various possibilities of circuits, and some of the simple ones which are used in op-amps I shall describe. Suppose you have a simple emitter follower plus VCC and then a resistance. This is your VI and this is V0. You should see that the level shifter does not change the gain. You took great pains in cascading DAs and a CCCS stage to make up a gain of the order of 10 to the 6th. Level shifter should not change the gain, and it should only change the DC level. You see that here the DC level of V0 is VI minus VBE. Agreed? This is a simple level shifter. You shift it by the amount 0.7 volts VBE. If you want more than 0.7, okay, then what you do is you use a circuit like this. The same emitter follower plus VCC, but you use two resistances, VI and V0, let's say R1 and R2. Okay, here V0 would be equal to VI minus VBE minus IE times R1. Agreed? But the disadvantage is, obviously by changing R1 you can shift it to by any amount, but obviously the disadvantage is that the signal itself gets attenuated by the amount R2 by R1 plus R2. We don't want this, and therefore we have to do something about it. What can be done is, one of the simple ways that can be done is to replace R1 by a Zener diode, a reverse biased Zener diode. Let's see how that looks like. Plus VCC, this is VI, and then you use a Zener diode here, a reverse bias Zener diode, and then an R2. The voltage that you take, output voltage is here. The Zener diode voltage is VZ with this polarity. It's a reverse biased. Obviously now V0 would be equal to VI minus VBE minus VZ. You choose the Zener diode properly so that the amount of shift is adequate. Does it affect the gain, signal gain? Does it affect the gain? No, because the Zener diode dynamic resistance is a very small quantity. Okay, RZ tends to 0, and therefore V0 signal component is approximately the same as VI. The other thing that can be done is, instead of changing R1 to VZ, let's keep R1 the same. These are various techniques that have been used in op-amps. So the op-amp design is as good as 30 years old now, 1964 or 65. It's 96, 30 years, and various techniques have been used. One of the things that has been used is, you keep R1 the same, but instead of R2 use a current source, I0. In any case you will have to use a current source for biasing. Okay, So why don't you use for the emitter follower also, and you take the output here, V0. Then once again V0 is equal to Vi minus VBE minus I0 R1. Agreed? What about the signal attenuation? Nothing. Why not? Because the effective impedance of this is infinity, and therefore there is no. This is also a very popular technique. Another technique that is used.
So, but if you use a current source for this,
Yeah.
active load, it has a finite impedance.
Finite, but if that is large compared to R1, okay, the minimum that you expect is R0, and R0 is of the order of 100K. Use this as 500 ohm. There is no problem. Okay. The one that is most sophisticated of this, well, one can also argue here. Let's go back a couple of slides. Instead of a reverse biased PN junction, that is a Zener, one could also use a number of forward bias diodes. Okay. For example, instead of the Zener, you could use like this to make up for the voltage. You could also use that. This has also been used in some of the chips. Particularly a Motorola chip is available in which several forward bias diodes have been used. Why forward bias? Why not a Zener?
This is on a chip, so we can make many diodes.
We can make many diodes. We can also make a Zener. A Zener is a costlier diode as compared to an ordinary diode. Why? Because it requires a heavy doping. It is to be specially made. On the other hand, a diode could simply be made out of all the transistors. You make 3 more transistors and make a connection. That becomes a diode. Okay? Right. Now the most sophisticated of this is what is called a VBE multiplier, a level shifter using VBE multiplier.
So how do you get a variable level shifting in the circuit shown?
Which circuit?
Any of the circuits?
Any of the circuits. Well, in this, for example, you vary this.
Can this not cause problems as far as dissipation and all that is concerned?
As far as
Dissipation is concerned.
dissipation is concerned, dissipation has to be kept within the limit. Of course, I0 squared R1 will be the dissipation here. This has to be kept within the limit. But please remember, these are not variable from outside. It's part of a chip. This is taken care of during the design. You know precisely how much shift you require, and you adjust to that. And once you adjust, you leave it at that. As I said, the most sophisticated one is to replace R1 by what is called a VBE multiplier. A VBE multiplier is a chip by itself. It's available as a chip also. And the circuit is this. Please draw with me. Not very complicated. We see same emitter follower. Instead of R1, you have a VBE multiplier, and the VBE multiplier, the circuit is like this: R3, R4, and then you have a transistor like this, whose base is supplied from here. This is Q2 and this is Q1, and the emitter is connected here. Then you have the R2, usual R2. R1, the place of R1 has been taken by this. The output is taken from here, V0. This is called the VBE multiplier. It's a very interesting circuit and has many uses in regulated power supply chips, in multiplier chips, analog multiplier chips, many other situations. This particular circuit is a very simple circuit, and it can be analyzed very simply. You see, this voltage would be VBE, agreed, between the base and the emitter. This voltage is VBE, and therefore the current through R4 would be VBE divided by R4. And if you ignore the base current, if the beta is large, then the same current flows through R3. Agreed? Same current flows to R3, and therefore the voltage between these 2 points, if we call this V1, V1 would be equal to VBE plus VBE divided by R4 multiplied by R3. That is equal to VBE 1 plus R3 by R4. And this is why it's called a VBE multiplier. You can multiply this 0.7 by any quantity that you require more than 1. Okay? By choosing R3 and R4 properly, you can adjust to any level shift that you like. Incidentally, the level shift here is V0 VI minus V1, no, minus VBE minus V1. So it is VBE multiplied by 2 plus R3 by R4. Is the point clear? Okay. So this is a sophisticated circuit and is very popular, very popular. However, I must point out that in the 741, the most commonly used op-amp is a simple emitter follower. Sometimes with a diode, sometimes not. It's a simple emitter follower. Okay.
Excuse me, sir.
Yes.
Can you show the previous slide?
Previous slide, yes.
Why do you need Q2 at all in this case?
This is the level shifter. This is VI.
You have shown VI.
This is V1. This is V1. This is the shift. This is the input. Now the $1 million question, I thought Ankur was asking that question. $1 million question is, what about the signal attenuation between VI and V0? Doesn't this act as a resistance? And there will be signal attenuation. So it is important to calculate the signal gain of this stage by taking the hybrid pi equivalent circuit, and if you do that, the signal gain AV is given by, what do you think, can it be greater than 1? Can it be greater than 1? No, because after all it's an emitter follower. It should be less than 1 if that VBE multiplier works like a large resistance. The gain, if you calculate, is given by 1 plus GM2 R2 plus R3 plus R4 divided by 1 plus GM1 R4. This is the overall gain. Does it fit the bill? Suppose, is there any obvious defect in this expression? Or is there a way to check whether the expression is? Suppose R3 and R4 are 0. Then the gain is, if R3 and R4 are 0, it will be a simple emitter follower. GM2 R2 divided by 1 plus GM2 R2. Okay? So it's correct. Now if GM2 R2 is much greater than 1 and R2 is much greater than R3 plus R4 divided by 1 plus GM1 R4, which can be very easily designed, you see that the gain, signal gain, is approximately equal to 1. Alright, so this is taken care of. VBE multiplier is very often used in an op-amp, level shifting. The advantage of this circuit, the advantage is that the shift can be adjusted. You can get any amount of shift. There is a disadvantage also. What is the disadvantage? Disadvantage is temperature dependence. The temperature, see, delta V0 delta T would be approximately equal to minus delta VBE by delta T multiplied by 2 plus R3 by R4. So if at all the temperature dependence of delta V0, the output, is amplified, what is this value, delta VBE by delta T? What is the value? 2.2, negative or positive? Negative. And therefore this is 2.2 millivolt per degree C. and if temperature changes, which it will, if it is in Delhi for example, very large change, the whole circuit will behave differently. Is there a way to compensate for temperature?
Yes, sir.
Yes, okay. We know this, to compensate for temperature. All right. We next consider the question of offsets, voltages and currents. As I had told you, the offsets occur because of mismatch in the input transistors, the two input transistors in the differential amplifier. And we can represent the offsets like this. We can model the offsets like this, that there are two currents, bias currents, let's call them IB1 and IB2. There are two bias currents, and in addition the two base voltages are different. So let's include this by means of a battery, VB1 and VB2. The problem arises when VB1 and VB2 are not identical and IB1 and IB2 are not identical. If they are identical, then there is no offset, and this is V0. This can be further modeled like this. We take the effects of these two offsets separately. That is, no more current. What we do is, we assume that there is a current source IB1 here, and that there is a current source IB2 here, and the difference between the two voltages VB2 and VB1 we model by a single voltage source. We call it VI offset, which is the difference between the two voltages with this polarity. Okay. Then as far as the op-amp is concerned, we can replace this by means of a single resistance, input resistance Ri. Forget about this triangle. If this voltage is Vi plus minus, then the output is, I have done this intentionally. What would be the output? AVI with what polarity? Which is plus? Down or up? Down. Okay. You must remember this, because I have said plus minus here with the inverting. This is the inverting and this is the non-inverting, R0. Okay. On Monday we shall analyze this circuit to find the effects of Vi0 and the difference between IB1 and IB2, and take some examples to illustrate this. Offset is one of the most irritating features in using an op-amp, particularly small signals, because the signals are comparable to offsets. Then you will confuse the output as due to the signal when it is actually due to an offset. Offset also can saturate the whole device, and therefore one has to be very careful.